subject, K-Python projector. It's a joint work with Giovanni Paolini, who's present there. And actually, I will introduce the problem, and he will continue with more details and more marks. So, I don't want to spend much time in the history of this problem, which is conjecture is very old, I think 50 years old. I will mention some names who made that conjecture later, but it was very considered very well known and important, especially in the subjects of singularity theory and of course hyperplane arrangements, geometric theory, and so on. Instead, so I profit of the fact that Giovanni is here to try to give to assume that not everybody is an expert on this subject. So I will start from a very nice example, which I think fits very well in this conference, which is the main example is just that of the break. So I want to give ideas behind the conjecture, and this is the starting point. So we have this break group with the standard representation. Sigma I, let me also draw this picture of rays taken by the classical Billman book, and the sigma i's are the elementary rays generators. This is verifications of relations, graphical verification of relations. Okay, so they have this break group, which is a very nice group, but there are other nice groups. This is the symmetric group, and the presentation of the symmetric group is just obtained by adding squares to the generators. SI are transposition I plus 1, and you have this you have natural surjection from break group to symmetric group. The kernel is the so-called pure break group. So there is another very interesting definition of break group, the topological definition as a fundamental group of configuration space. Configuration space is just the space of n unordered points in a plane or a disk. Okay. And also we have another configuration space for the pure group, which is the space of orders. So this is a topological definition of this group. But it's convenient to understand the situation by introducing the hyperplane by diagonal arrangement of the IA. So the configuration space clearly is the same as the concept of the arrangement, Cn, and then you have the function here, which is just the coordinates of Cn, and you see that the reaction is pretty exactly on the component of the only points non-understood. So you can take the space, and the situation is given by this covering. You have a regular group sigma n, and okay, this is an interesting situation for the break group. which also has much more stronger topological. This is very well known, at least from the knowledge. The configuration space is a K pi. That means, of course, that the higher amount of the groups are theta. It is a very strong topological property of spaces. Okay. Very interesting. And in these cases, it's really very easy to prove because just by induction, you can have relation with pi is a K by 1, so that's this case. So you have this very strong topological property for the configuration spaces. Let's see the action on the symmetric group as a particular class of groups which I am going to introduce. And this action is the action of a reflection, so-called reflection group in Artin. Reflections are orthogonal in this case with respect to the standard symmetric product, for example. Okay, this is a reflection group, so a group generated by reflections. And for example, the transposition Ij is a reflection with respect to the diagonal hyperplane Hij, Zi or Z. Okay. Now, as I said, I want to generalize this expression, and I want to introduce other classical objects, so Conjecture groups. This is something which is codified by set S, and numbers, integral numbers. MSS is 1, the others are at least 2. And of course, you can codify this by a graph with vertices S and weighted graph. The edges are weighted by these numbers, MS. And then classically, you have this Conjecture system, which is given by a pair WS. W is a group which has this particular presentation, which involves only pairs of generators. It is convenient to change a little bit this presentation by writing the squares, S square equal 1 evidence. And the other generators are given by equality of 2 words involving pairs of generators, the same number of factors, which is 5. Okay, this is a standard presentation of the Conjecture group. And classically, these groups are classified, these affine groups are classified by some list of graphs, and they correspond to reflection groups. So finite reflection groups, which is you have an arrangement of hyperplanes where each hyperplane is a fixed point set of mirror set of some reflection. And this arrangement also stratifies the space, and the maximal dimensional strata are called chambers, which are the components of the array. So it's also you have that generators of the group are in one-to-one relation with some with the reflections with respect to the walls for some chamber. Okay, for example, okay, and we will need also a set of all possible fractions of the group, which correspond to all possible conjugates of the standard Coxeter generators. For example, this is a trivial example, maybe this example of symmetric group with two generators, two Coxeter generators, and three reflections. Okay. So I want to generalize to see if these groups have the same properties they break. So you have this complexified hyperplane arrangement. This is the configuration space. You have an action of W on this configuration space. So you have some orbit configuration space as before, the case of brace. And we introduce now this other class of groups which are called Artin groups. This is done for any Coxeter group. So start from any Coxeter group with the presentation which I wrote before. You cancel the squares of the generators, these relations. And it remains this kind of relations which define a new groups which are Artin groups. So, of course, if you take if you start from the symmetric group, you have the break. So, also these Artin groups have a topological definition. These are also the fundamental groups of these configuration spaces. This was known at least, I think, in many cases by Bristol. And so people asked at that time if such groups had the same very strong property that this configuration space was also K5 This was shown in a famous paper by Inven, and after some few cases were already proved, some cases were already proved by others, by case proof. And of course, they lean to a little bit more because Steven was about simplicial arrangement, but I don't want to say more about it. That's so. This is even these finite Coxeter groups have this very strong property that its orbit configuration spaces are K by 1.
Can you say again exactly what you have to show the K by 1 space? Like what do you mean?
Yeah, the definition is that the pi 2, pi 3, and so on is 0. Or equivalently, you can say that the lesser covering is contractible.
Okay, so we need the fundamental group, like the level 1 to
Yeah, only fundamental group, and then nothing else.
Okay, thank you.
Also, very strong property. You think of a CW complex is equivalent to think that universal group is contractible. Okay. Okay. Then we have finite Coxeter groups, but most of Coxeter groups are not finite. So you have analog construction for all Coxeter groups. I want to spend more words on affine reflection groups. And these are Coxeter groups realized as groups of Euclidean reflections on the affine space, Euclidean affine space. For example, this is the case of Pisa with numbers which characterize the group. And this dark chamber is the chamber where the reflection with respect to the walls are identified as 1, 2, 1, 2, 3. Okay. And of course, also these groups are classified by okay. And by some list of graphs. And then we have similar topological constructions. You have configuration space, which is a complement of classification. And even in this case, you have a free action of the group. You have orbit configuration space. This is the easiest example of E1 theta, which is as a group, it is just Z. The configuration space before taking the quotient. And also in this case, you have this topological characterization. These are fundamental group of this orbit space is the Artin group, which I introduced before. This was known since 80s. Can be recovered, I think, in an easier way, by some later works, but it's not important now. And then you have this conjecture that the orbit configuration space is also K5 space, which is a strong property about the orbit space, which is similar to the case of rates. I think the conjecture is attributed essentially to an odd tone and can be stated in some technicalities for all articles. Okay. Some cases we already know, of course, since 9, but all the proofs are very different and case by case. So we proved for finite groups with essentially case-free. So these conclude probably the main class of Artin groups, which are the Euclidean Artin groups. Giovanni will talk about something else, something more, something like that. These are the main classes, the finite and the finite. And okay. Of course, we sent the our theorem to the linear. We received a good feedback. That's good for us. Don't want to, but satisfactory. Okay. I want to come back to the proof of the final case, which Paolini did, but not exactly in the same way, but very similar way, just the same philosophy and same methods. And the main ingredient is the so-called gut-sided theory, which Paolini implicitly used by some paper, gut-side paper of the 60 or 70, I don't remember now. And after the Paolini proof, it was developed formally by many people, and now it's called gut-side theory, gut-side groups, and so on, which are more or less groups where the Paolini proof works. That's more or less equivalent distinction. joking, of course, but there is some very precise definition which I don't want to say exactly, but the precise structure on a group is there given by monoid and a special element, which is called the precise element, with some list of axioms. First of all, the monoid is cancellative, left and right cancellative. And okay, any two elements have LCM and CCD on the left and on the right, the monoid, with respect to the relation of divisibility. By say that some element divide another is third element, divide by first one is the second. Okay, and this special element delta is such that all these divisors generate right and left divisors are the same. More, there are other technicals which I skip, and then this monoid is included in G, and G is group of fractions of this monoid, which means that every element of the group is written as the inverse of an element of the monoid times another element of the monoid. And the Gaussian structure is good in a group, because if you have a Gaussian structure, for example, you have a kind of normal form of this kind. Not exactly, this is more specific, but more or less is a kind of some power of the special element times an element of the monoid. And this allows you to solve, for example, the word problem. So if you have that structure, it's done some classical problems in the group. How to produce that side structures? If you have a group, you can take any group, not just a constant. In any group, if you have some generated set which is symmetric, then you have this length, standard length of an element, the minimum number of factors in factorization of of course, the length depends on the set of generators which you choose. And this group, the group becomes soon a poset with this relation. This relation is equivalent to say that some minimal factorization of y begins with the minimal factorization of x. More or less. Okay. So we have this structure of poset of the group given by choosing some set of operators. And we say in this case that x divides y, this relation. Okay. Now, this, if you have this or further technical property, which is always satisfied if the element G, if the set of generators is stable under conjugation. So we have because this kind of element, a balanced element in the group. Then let's consider the interval. So the set of elements which divide this balanced element. So this is the interval in the poset which we introduced before. Between the unit element and G. Okay? Now, using this interval, we introduce a new group. So we have started by group G. Now we have an element small g. We introduce another group, which is related to this interval. So we call it that interval. This interval group has the generators, just the elements which divide it. So between all the elements of the group, take the elements which stand in the interval. Right. And the relations, so you can think in this way. You have this interval to set, and you have the so-called Hasse diagram of the set. That is the edges of this set are labeled by R, by the generators. Okay, and then you read inside the Hasse diagram two parts which have the same ends, and you have some relation. All these kind of relations. And this is a presentation of a new group. And, okay. You have this new group which is related with this interval. Then there is a theorem, more or less at the beginning of 2000s, by Bessy. If this interval is lattice, meaning that each element has LCM and if this combinatorial property works, then the group which I defined before, this presentation is a graph cycle. That's very nice property, which is you connect some combinatorial property of the interval with the structure of a group. Of course, the García structure here is given by monoid M, which has the same presentation of the group, and the consequent element is just this G. And another feature of these García groups is that you can construct explicitly say some reduced bar complex in some sense. This is some explicit k by 1, which is similar maybe to the bar complex, but is much smaller. And very, so I give some words about that. In the case of interval group, can do in general, but in case of interval group and balanced element, you have a delta complex, CW complex, which is a delta complex, such that the simplices are just the sequences x1 and xp, where xi is in the interval 1g, so it's a divisor of g. And this sequence is a piece of some minimal factorization of G. Okay. So these are the syntheses, more or less, and phases of these syntheses are obtained either by removing the first or last element of the simplex, or multiplying to consecutive elements of this individual. Okay. So it's similar to the bar complex, but very much smaller because it contains much less elements and so on. Okay. So let's do. So this is an explicit. You can want to show that this, which I define as a k by 1 general for a García let's go back to Coxeter groups. And are a set of simple reflections. In the finite case, any finite group, it's well known to have a unique longest step in a finite Coxeter group, which corresponds to a gallery which in the arrangement going from some chamber to the opposite chamber. Okay, so you have a unique longest elements, and you have several facts here. If you consider the interval 1 delta, in this case, and the interval group W delta, which is connected, associated to the 1 delta, this is isomorphic to the standard Artin. This is not difficult to see because the relations are the same. The interval is lattice. So this group is a that side group. So the Artin group is a that side group. And the interval complex is equivalent or multiply equivalent to the orbit configuration space. This is essentially, this last point can be done, for example, by an explicit equivalence with some known other complex which are the same homotopy equivalence. So this is essentially more or less some difference, but it's essentially the proof of widely on the A.1 case of finite concept. Okay, so for example, there is a paper for this last one. Okay, so now there is another question. You have a group, you have some Gaussian structure, but is that unique Gaussian structure? No, there is another Gaussian structure which is called the dual Gaussian structure. There are, even in the case of finite Coxeter groups, if you change the set of generators, enlarge the set of generators and take all possible reflections, all possible conjugates of the Coxeter elements, and then you have different Gaussian structure, choosing also different Coxeter elements. Just to take a so-called Coxeter element of the group, there are many, but in many cases these are called conjugates, and actually in the finite case this is true. But okay, take just a Coxeter element. Remind you that this is the you can define that by choosing a chamber and take the element which is given by the product of the reflections of the walls of the chamber, some order. Okay. There are some facts. The dual, so if you take the interval 1W, you have the interval group associated to this interval 1W, then even in this case, the dual group, so-called dual group, is the isomorphic to the standard Artin group. This was proved in case AN by Billman colleague, and in general by BC. The interval 1W is also lattice. Okay. And so you have another Gaussian structure on the same group. Okay. I've been chosen different generators and Coxeter elements. So you have that this KW is a K by 1 by the Lie theorem. And so this is also multiply equivalent to the orbit space. So this is a K by 1 by the what I said before, that is a Gaussian structure. By the Lie theorem, this is multiply equivalent to the orbit space. Okay. So we have this in the finite case, at least two Gaussian structures. So, in the, for example, in case A2, you have three reflections. The interval, the Hasse diagram of the interval 1W is given by this picture. W is the Conjecture element. And the dual group is presented in this way, which is very easy to see that this is the same as the three by eliminating the S3. Okay. So, what happens in the affine case? Many people try in the past, I had one of these, to prove, to generalize the lead proof by using the same methods. But unfortunately, it doesn't work because the standard, the standard structure is not Versailles structure because you don't have, it doesn't exist the standard structure because you don't have the longest element. We are fine case. There is no longest element. The fine case length is going to be fit. So. Okay. Now, people try to use the alternative Versailles structure because you always have a Coxeter element. In any Coxeter group, you have a Coxeter element. So one can try to use the alternative, the dual structure, to see if this works. Okay. There were very recent interesting papers by McCammon and Charlie, and our proof is based on some the results that they have. And let me say a few words what they did. They find finite dimensional classifying spaces, but not finite as a constant, infinite number of cells for their finite groups, but they do not succeed to relate these complexes with the ordered spaces. So this is just an abstract construction, interesting construction, which gives already some good consequence, like torsion-free property and so on, but it is not connected with the K-1 conjecture.
So what is cosmological dimension? It's
just the length of the interval, E plus 1 minus 1.
in the fine case.
Sorry?
In the fine case,
Fine case. Yeah. Yeah, the maximal dimensional sets are just a maximal chain going from 1 to down. So more specifically, they use that take a Coxeter element and try to see if this interval, as in the finite case, is a lattice. Unfortunately, this is the lattice in very few cases, which they classify. And these are, if I correctly, there are C and G, and only one case in ANT. In all other cases, this is not. There is a precise way to see when there is when the lattice is when the interval is lattice. I think Giovanni talked about that. But this is, since this is not lattice, then what they did is try to enlarge the group such that the previous interval embedded in a new interval, which is a lattice. That's the trick that they succeeded to do. So they found that they added some new translations, new geometries to the Conjecture group, and found a new bigger group such that the new interval is a lattice. That means that by what I told before, that the interval group related to this new bigger interval is a Gauss-side group. And also they show that it is a inclusion. They also showed that the interval group, which I introduced before, which is defined by the interval 1W, is isomorphic to the standard Artin. So you have an interval complex related to the bigger interval, which is a k by 1, because this is a lattice, is a lattice property, is a k by 1. And this is a finite dimension, a classified space. For the bigger group. Of course, this produces some k by 1 also for the Artin group, which is included, because you just take the coverage which is connected with the inclusion of the groups, and you have some complex, but which is very infinite number of sets. Okay, so that's more or less what they did in a few words. And I think okay. So let me just mention very quickly what are the three main steps of our proof with practically no detail, which I and these are some order of these steps. This first we show that this KW, which is the complex, which is associated to the interval 1W in the original W, is a classifying space, even if the interval is not a lattice. Okay? That's maybe the less combinatorial part of the paper, which is very combinatorial paper. Okay. So this is done by splitting the complex, the biggest complex, in two pieces, applying some trick. Okay. So this is the first property. So you have always a k by 1 space with the fixed interval 1W, original interval. Then we introduce another complex, finite complex in this case, which is defined in this way, easily defined in this way. Take a fixed channel, assume that the group is product of what of the reflection of some fixed channel, C0. And then you consider only simplices, x1, xd, such that the product stabilizes somewhere this channel. That more or less is the finite complex which we consider. This can be the affine case. You can do that in many cases, but in the affine case, like that. Of course, this is a subcomplex, and the finite subcomplex of the integral complex. And we had to show that this finite complex is homotopy equivalent to the configuration space. And this is also done by parallel with some previously known complex, which we knew which were homotopy equivalent, by explicitly by some more or less explicit, I mean stepwise construction of homotopy. So I also skip that. Giovanni is more. And these all the complex, just to say, these all complex in the case of fine case, or fine collection groups with the rank n+1 looks, for example, this is the case A2 theta. There are three hexagons with the identification on the faces. It's all complex, which turns out to be a k by 1 by the proof of the and these are the x prime is also k by 1 by the proof. And then the very last step is to find a deformation retract from the big complex, infinite complex KW to this finite subcomplex. This is the most combinatorial part. We use discrete, heavily use discrete Morse theory, and in doing that, we also control the matching in this Morse matching in this part. It was very useful to find another probably very interesting side result, which has some interest, at least in combinatorics, which is that the interval is offset 1W is shaped, which is a classical property of combinatorics, very powerful property in combinatorics. And this was very useful. This result is interesting by itself, and it was very useful for us to construct this match. And okay.
Mario, if you can interrupt for a second.
Yeah.
So use this shellability to show that a certain space is contractible.
We used to define this matching.
Yeah, but topologically, it doesn't mean this space is contractible, which is what you try to
No,
show.
no. This is another problem. This is just a problem of this offset.
That I understand, but does this is the step towards showing the universal cover of the classifying space of this element is a K by 1, that it's contractible?
This was, if you want, technically useful for us to construct this matching for the contraction from big complex to the small complex. Okay. So you have to construct a retraction, formation retraction from this space to this. Okay, as well. So we did that by Morse theory, discrete Morse.
Okay, I understand.
Discrete Morse theory, so you have to control, you have to define a matching, a perfect matching on the complement of this space. There are two steps actually. It's not. I'm skipping many details. I think Giovanni will talk on this of speed. It's just an idea, which is the speed Morse theory and or the main results. I think that also the result is interesting. Combinatorics, for example, it was studied in the final case. It was good that the final case was I forgot, I think, Salvetti probably. And, of course, from just so I think just remark that from our theorem it follows also another different proof that the dual proof, which is defined by this presentation of the integral, is isomorphic to the standard. And then, of course, okay, for these steps, give the proof, which running with time more. And of course, there are still problems. This doesn't finish everything because you have all the other groups, considered groups which are not known in general. And there is a series of problems which comes to see. Essentially, if all the technical proofs which we use can be generalized, that's all. Okay. Thank you.